Welcome to this lesson on derivatives of basic functions. In this lesson, we're going to learn the rules for computing different derivatives symbolically. Many of these functions you've already seen in the previous units, and we're just going to talk about simple shortcuts for finding those derivatives that we've been estimating graphically and by using tables and other computational means. So we'll look particularly at constant functions, the power rule, the constant multiple rule, the sum and difference rule, and we'll put those together to be able to find derivatives of polynomial functions, and then we'll also look at finding derivatives of logarithmic, exponential, and trig functions. The first rule, the constant function rule, is pretty straightforward, and most of you could probably guess this at this point. If you have a function f of x that's equal to a constant, so if you think about that graphically, that means you've got some function right here where all the values of the function are a constant c, and you want to think about what the derivative of that function is. Well, the sensitivity or the change in the output variable is going to be 0. You can also think about this in terms of slope. So this function has 0 slope everywhere. So we would say the derivative of f, or f prime of x, is 0. A couple examples. If f of x is the constant function 3.5, then just according to the rule, f prime of x is 0. Similarly, if you have a function that describes the population for the state of Minnesota, and if that population happens to be constant, then you can think of the rate of change of the population, or the derivative, being 0, because that population is constant over time. An equally easy rule for finding derivatives is the derivative of a linear function. If you've got a function f of x equal mx plus b, if you remember what that would look like, the b indicates the y-intercept, and the m, the coefficient in front of the x, indicates the slope. So that might indicate something like a line with slope m. So if you think about what the derivative is, if you interpret derivative in terms of slope of the graph of a function, then the slope of a line is everywhere equal to m in this case. So the derivative of a linear function is just the slope. A couple simple examples. If f of x equals 5 plus 2x, well, the slope is just the coefficient of the variable x, so f prime of x is 2. Similarly, if you have modeled the price per barrel of oil at year t, and you have that price is 30 plus 1.7 t, where t is the number of years after 1980, then the rate of change of price, or the derivative of price, is going to be just the coefficient of t. So we'll have p prime of t equal 1.7 in this case. Okay. So making things a little more difficult, we can get to the power rule. So now you think about functions f of x equal to x to the n. So these might be functions that look like parabolas, f of x equals x squared, or cubics, f of x equals x cubed, and so on. You may have seen this rule before, but it's pretty straightforward, and the idea is if you're looking for the derivative of x to the n, the rule is you just take that power n and bring it down as the coefficient in front of the x, and then you just subtract 1 from that power. So you wind up getting f prime of x equals the original power times x to the power minus 1. So if we look at a couple examples, if f of x is x to the 7th, then how do we compute the derivative? We just pull that 7 down in front, we subtract 1 from 7 and get 6, and we find that f prime of x is 7 times x to the 6th. Now, I'm not going to go into the nitty-gritty of why all of this works, but this rule works if you have other integers, other numbers for the power besides integers. So if we want to think about the derivative of the function square root of t, we can think about square root of t as t to the 1/2 power, and then use the power rule. So the derivative would just be the derivative of t to the 1/2, which means you pull down the 1/2 in front of the t and subtract 1 from the power, and we're left with 1/2 t to the negative 1/2. So that's the power rule. Okay, now we want to start putting some of these rules together with other rules, and one of those things we can do in that way is use the derivative of a constant multiple. If you have a function that you're wanting to find a derivative of, and that function happens to be a constant times some function you know. The rule here says you can just pull the constant kind of out, compute the derivative of the function as you would before, and then put that constant back in front of the derivative. So for example, if we look at the function 3 times x to the 5th, we know from the power rule how to compute the derivative of x to the 5th, so we just let the 3 kind of hang out. We compute the derivative of x to the 5th and get 5x to the 4th, and then we multiply that 3 and that 5 and we get 15x to the 4th. So this is a pretty straightforward rule. These two rules are also pretty straightforward. The idea here is if you have a derivative of a sum or a difference of two functions, you can just compute the derivatives of the functions separately and then add or subtract them. So let's take a look at an example here. If we have the function h, which is the sum of actually three functions, 2x, square root of x, and x cubed, then the rule basically says, don't worry too much about any of the details, just look at each piece individually. So the derivative of 2x, that's a linear function, that's 2. The derivative of x squared, we just computed something like that. That's similar to x to the 1/2. So we can use the power rule on that and write down 1/2 x to the negative 1/2. And then again, we can use the power rule on x cubed, pull down that 3 and subtract 1 from the power, and we get x squared. And the sum rule says just add those up. Similarly, if you have a function r of q that's modeling revenue in dollars from producing q units of a product, and if r of q equals 1,000 q minus q squared, then we can use the difference rule here and say the derivative of 1,000 times q is just 1,000. The derivative of 3q squared, you use a power rule again. The 2 comes down, the 3 and the 2 multiply, and you get 6q. And this difference rule says you just subtract those. So the derivative r prime of q is 1,000 minus 6q. Okay, so we've got a couple more functions left. The derivative of the exponential, this is an important one in calculus. So if you think about the exponential function p equals e to the t, we might want to think about what the derivative would look like before I tell you what it is, if you haven't seen this before. So if I think about derivative in terms of slope, you might think of the slope right there as being a slightly small positive number. The slope there, still positive, but it's a little bigger than the previous slope. And so what you might notice when you look at the exponential function is all the slopes are positive, so the derivative should be positive. And all the slopes as you move from left to right are increasing. That this slope here looks a little bigger than that slope here. So that might be a slope, for example, of 5, and this might be a slope, for example, of 2 or 3. So we're looking for a function that's positive and increases as t increases. And it turns out that the exponential is precisely the function whose derivative equals itself. So the big theorem here is the derivative of e to the x is the best thing you could hope for. It's just e to the x. We can talk a little bit about how this works and why, but later. But similarly, if you have the derivative of another exponential function, say 2 to the x or 10 to the x, that derivative is the constant log of whatever that base was times a to the x. So we'll look at a couple of examples, and this will be pretty straightforward. Okay, so let's look at a couple examples. If f of x equals 3 e to the x, then f prime of x should be also 3 e to the x. We're using the constant multiple rule, so the 3 just hangs out, and then the theorem that says the derivative of e to the x is just e to the x. So that one's pretty easy. If we're interested in the derivative of 2 to the t, we have to use the rule that said the derivative of a number to an exponent is the natural log of whatever that base number was times that number to the exponent. Okay, in a previous lecture we actually found an exponential function that modeled a bacteria population, and that population n at time t was 1.3 to the t, where t was a time in hours from the start of the experiment. And we actually asked you to estimate some of those changes, the sensitivity of population to t, but now that we have these rules, we can compute those very quickly. So if I want to know what the rate of change of that bacteria population is, I can immediately say, oh, this is an exponential function. The rule says the derivative should be log of 1.3 times 1.3 to the t. So I get m prime there. So for example, at time 3, at 3 hours past the start of the experiment, the rate of growth, which would be n prime of 3, so now we're just plugging in 3 for t, is going to be log of 1.3 times 1.3 cubed, and that's about 0.586. And in the model that we talked about before, this was in hundreds of bacteria, so this is, when you think about the units, that would be hundreds of bacteria per hour because it's a derivative. It's a rate of change. Okay, so natural log. If we know how to differentiate exponential functions, we should know how to differentiate natural logs because they appear often in the life sciences. And the rule is pretty simple here. The natural log of x, if you want to take a derivative of that, it's just 1 divided by x. So if we look at some examples, if we have f of t equals e to the t plus natural log of t minus t to the 8th, this one has just about all our rules in it. The derivative of e to the t is just e to the t. The derivative of natural log, according to our new rule, is 1 over t. And the derivative of t to the 8th, we use the power rule, is 8t to the 7th. And then we're using the sum and difference rules here to put them all together. Similarly, if g of x equals x squared plus natural log of x, then the derivative, it's pretty easy to see, is just 2x plus 1 over x. Okay, so the last two functions that we're going to learn some derivative formulas for are sine and cosine functions. And those are pretty straightforward. The derivative of the sine of x is the cosine of x, and the derivative of cosine x is minus sine of x. So a couple of examples for computational purposes. If h of t is sine of t plus 3 cosine of t, then h prime, well, the derivative of sine of t should be cosine of t, and that's right there. And here we've got a constant multiple, so the 3 kind of hangs out for a little bit. And the derivative of cosine of t is minus sine of t. And so we've got the minus 3 sine of t right there. Similarly, if f of x is e to the x plus sine of x, then f prime is e to the x plus cosine x. Okay, so after this module, what I'd like you to ask yourself is, can you compute the derivative of a constant or a power function? Can you compute derivatives of polynomials, exponentials, and log functions? Can you compute derivatives of sine and cosine functions? And can you use the sum and different rules in a variety of settings? All right, well, thanks for listening.